PC1 sends a frame to PC2. As soon as the switch identifies making a decision. 4 jumbo frames. This could be up to 9,200 bytes. Welcome, everyone. Today we are going to explore the fundamental mechanics of how data moves across a network, specifically focusing on the TCP IP model and the critical process of frame forwarding. Let's start with a high-level overview of how the TCP IP stack works. At the application layer, we start with raw data or a message. As it moves down to the transport layer, we add headers like TCP or UDP to create a segment and perform initial error checking. At the network layer, we add IP addresses to create a packet. Once we reach the data link layer, we wrap that packet into a frame by adding MAC addresses and a frame check sequence, or FCS, in the trailer. Finally, at the physical layer, everything is converted into bits, zeros, and ones to be sent over wires or wireless signals. The trailer and FCS are vital because they ensure the integrity of the data throughout its journey. Now, let's zoom in on the frame itself. A frame is the basic unit of data for local network communication. Think of it like an envelope. Inside is the message, and on the outside are the MAC addresses for the sender and the receiver. These physical addresses are what allow a switch to intelligently direct traffic. When a frame hits a switch, the switch inspects the destination MAC address to decide exactly where that data needs to go, a process we call frame forwarding. The frame forwarding process can be broken down into 5 distinct steps. First, host A prepares the frame by attaching its own MAC as the source and host B's MAC as the destination, along with the data and error checking trailer. In step 2, when the frame arrives at the switch port, the switch doesn't just pass it through, it actually learns from it. It looks at the source MAC and updates its internal MAC table, noting that host A is connected to that specific port. In step 3, the switch looks at the destination. If it already has host B in its table, it sends it to the correct port. If it doesn't know where host B is, it performs flooding, sending the frame to all other ports to find the recipient. Moving to the final stages. In step 4, the switch directs the frame out through the specific port associated with host B. Finally, in step 5, host B receives the frame. It immediately checks the FCS in the trailer to ensure the data wasn't corrupted during transit. If the calculation matches, it reads the message. If there's a mismatch, the frame is simply discarded to prevent errors from spreading. It's important to distinguish between flooding and broadcasting. Flooding occurs when a switch doesn't know the destination MAC and sends the frame to all ports just to locate it. Broadcasting is intentional. The frame is meant for everyone, so the switch automatically sends it to all ports. Regarding speed and reliability, we have 2 main methods, store and forward, where the switch checks the entire frame for errors before sending, and cut through, where the switch starts forwarding as soon as it reads the destination MAC. While cut through is faster, it relies on the host TCP layer to fix any errors that might have slipped through. To manage this efficiently, the switch maintains a dynamic MAC table, updating it every time it sees a new source address. This learning capability is what makes switches more efficient than hubs. We also rely heavily on the FCS for error checking. If a frame is corrupted, the switch discards it, and it's up to the higher level TCP protocol on the host machine to request a retransmission. This ensures the network remains clean and reliable. Let's look at the structure of a frame in the context of store and forward switching. Here, the switch must receive the entire frame, from the 8-byte preamble all the way to the 4-byte FCS checksum, before making a decision. 4 jumbo frames. This could be up to 9,200 bytes. This method provides the highest level of security and error prevention because the switch validates the CRC before the frame ever leaves for its destination. In contrast, cut-through switching is built for speed. As you can see in this diagram, the switch only needs to wait for the 6-byte destination MAC address to arrive. Once that address is identified, the switch begins forwarding the frame immediately, even while the rest of the data is still being received. This significantly reduces latency in high-performance environments. This diagram illustrates the cut-through process in action. PC1 sends a frame to PC2. As soon as the switch identifies the destination MAC, associated here with port FA0/2, it opens the path. The load, or data, follows right behind the header, minimizing the time the data spends inside the switch. Here we see a scenario where PC1, MAC AAA, is sending data to PC3, MAC CCC. The switch checks its table for CCC and finds it on port FA0/3. Even though PC2 and PC4 are on the same switch, they won't receive this data because the switch has already learned the specific port mapping for these devices, preventing unnecessary traffic on other segments. Returning to store and forward, let's look at the role of the sender. PC1 calculates a cyclic redundancy check, or CRC, and places it into the FCS field. The switch then receives this entire package. It performs its own calculation and compares it to the FCS provided by PC1. This handshake of data integrity is what keeps our communications accurate. To clarify the technical details, the CRC is the mathematical result of the frame's data, while the FCS is the physical field in the frame where that result is stored. It's important to remember that the switch doesn't create a new CRC. It simply acts as a gatekeeper. If the check passes, the frame is forwarded. If there's an error, the frame is dropped right there at the switch. Finally, let's look at a broadcast scenario. If host H1 needs to send data to every host on the network, it uses a special destination MAC address consisting of all FS. At the IP level, it uses the broadcast address 192.168.1.255. When the switch sees this all FS destination, it knows to duplicate the frame and deliver it to every single device connected to the network, ensuring the message reaches its entire audience.